Please.
Thank you. My name is Eike Lorenz. I'm from the Institute of Integrated Production in Hanover. We are a non-profit organization and a affiliated institute to the Leibniz University of Hanover. And we conduct research in multiple areas. One is my project, or the project I'm assigned to, which has the goal of determining the rotation angle and torque contactless and ideally optically. And thank you to the Austrian Institute of Technology for the opportunity to talk about this today. So starting with a little bit of background and to provide a bit of motivation why this would be important, why do we want to measure rotational speed and torque. Anywhere where we use a rotating shaft to transmit power, we need these two values to provide control, to provide predictive maintenance, or values for the predictive maintenance, or condition monitoring. This might be the two logos on the left describe the generators in wind turbines or hydro power plants, but also in the maritime sector, the ship's propeller has a shaft, the fan shaft in the jet engine, or in a car we have the cardan shaft which transmits power. And all of these shafts need some kind of measurement to know the torque and the rotational speed. Oops. Sorry. Now, so this is nothing new, and why do we invest time in researching new technologies here? We already have sensors for both of these measurements. On the left you can see a conventional rotary encoder to measure the rotational speed, and stain gauges usually provide the torque measurement. So why do we need something contactless and something new? These two sensors have two disadvantages. The first big one is they're not contactless. So you need to attach them somehow to the shaft, which is cumbersome. You need a lot of labor to do so, and in case of the stain gauges, it's also very complicated to do it very precisely. So they have the first disadvantage, it's not contactless. You have to attach them, and the second disadvantage is you have two sensors for both of your measurements. So it would be better to have an integrated measurement and a contactless. What kind of contactless methods could we use? What physical properties could we use to measure these two variables? Rotational speed can be measured contactlessly in different kinds of methods, and torque as well, but they have one in common, which is the optical property. So the optical measurement provides the possibility to have an integrated method which both measures rotational speed and torque. This is something at the Institute what we are now researching, or where we are now working on for the past 10 years already. Starting with Integrat in 2014, it was the first research project where we laser engraved barcode markings on a chrome or normal steel shaft, and this provided us the rotational angle at two positions, and if there would be a moment attached to this shaft, we were able to measure this. And 5 years later, the next research project was called MiniVip. It downsized the whole sensor setup quite a bit and also increased the stability against vibration. And now, we still were reliant on these laser gravings, which were also very difficult to engrave precisely on this curvature of the shaft. So we want to go away from this barcode style engraving, and we only want to use the naturally occurring features of the steel surface of the shaft. So here you can see the surface of or how the surface looks from a steel shaft like that, and already on the first glance you can see a lot of features that might be that we might be able to exploit to determine the rotational angle. And this modification-free approach I want to show you on this scheme here. In the center you can see the torsion shaft, which transmits the power. And so if now power is transmitted via this shaft and you have a torque applied there, you have a angle, the torsion angle. This torsion angle increases with the length of the shaft. And if we measure now the difference of this angle from one point to the another point with a fixed length between that, so phi 1 and phi 2, we can then compute back to the moment. How do we want to do this? First, for each cut out section here, we want to create a panoramic surface image. This is seen here on the bottom. And so we map all of these features that occur on the shaft surface and map them to a single angular value. And then when new images come from each camera, we can match those to the panoramic image and find out what the corresponding rotational angle is. And then if we have the two rotational angles, we can then again determine the phase difference, and we know the moment. We divided this project in 3 sub-goals. First, we create this panoramic images of the fan surface. Next, we want to investigate feature-based matching algorithms to match the occurring features, the occurring frames to the panoramic image. And lastly, evaluate that under different conditions. Here, I hope this works, you can see what the camera sees. We use a 12-time magnification, and you can see already there are a lot of features or characteristics we might be able to exploit for this operation. And I hope another thing is now visible, and this is the unroundness of our used. Now you can see that it gets blurry, and this is caused because we have this high magnification, and we're very sensitive to any distance changes between the surface and the optics. And another real-world problem that you can see now are these dark spots. This is pollution, either on the optics or even worse on the surface. So then why do we need this high magnification? The shaft is round, and we want to mitigate or minimize any effects by the curvatures or any projection errors as much as possible, and have a flat surface, or the surface should be as flat as possible that we use for our operation. I'm just going to let this play out. After that, we go back to 360 degrees and it gets sharp again. So the first step was creating these 360 panoramic images, and for this we use consecutive images. So image 2 follows image 1, or image 1 is precedes image 2, and they both have an overlapping part. This is shown here in this yellow part. It shows the same part of the surface image, of the shaft surface. The red part is only visible in image 1, and the green part is only visible in image 2. And from these consecutive images, step by step, we create this 360-degree panoramic image. Down here you can see the section made up only by two images. If now a third image would come up, it would be then again matched to the panoramic section. How is this done? This is right now done by cross-correlating these images. Some first insights. Here you can see the apart from the panoramic image, if there's a tilt in the camera. So as you can see, the resulting panorama is very skewed, and you get a lot of black pixels that are very useless and only take up valuable information, computational power. For the accuracy, this is a bit complicated. This graph, what I tried to show here, on the x-axis you can see the images, 720 images, and on the y-axis you can see the offset between each image. And between each image we rotated the shaft by 0.5 degrees. So we would expect that the offset is steady at 0.5 degrees, but it's not. And we're wondering why was this the case. We thought maybe it's because of the unaligned camera, which was tilted, but it turns out it was the transmission by the worm screw. So the worm screw turns 48 times to turn the fan shaft, or to turn the shaft one time. And this is exactly what we can see here. So our method was actually accurate. It was just a mistake on our end that we thought it was something else. And it proved as an accuracy test at the end. So what we can see here is a first test that, or first proof of concept that we have an accuracy of less than 0.02 degrees. Now we want to go back away from this. So this was the first sub-goal, and we want to move to the second sub-goal, which was the feature-based approach. Feature-based approach we can divide into these four groups: detection, description, matching, and outlier filtering. And for this, again, I have these two images that we already know already. So between image 1 and image 2, the shaft is rotated by 0.5 degrees. And we want to find correspondences between this. We use the scale invariant feature transform algorithm to find possible key points and describe them. And all these blue dots are possible key points that might be exploitable for the image matching. Now we don't want to use every, so we can save some computational power. So we only use the 50 best. These are then matched by a very brute force similar method, the k nearest neighbor method. And as you can see already, the 50 best matches appear to be quite reliable. How can we see if those are truly positives and not false positives? The more they are parallel to the direction of the shaft rotation, the vector down here, the more confident we can be in these matches. So just for an example, I can show you a false positive. It looks like this. So it's angled towards the rotation vector, and also you can, by just the first glance you can see this is obviously not the same point. This is our future, the things we want to investigate in the future, this feature-based image matching, to make our method more quick and more reliable. And this also already concludes my presentation. Myself and my colleague Niels Jansson over there, we both work on this project, the project homepage you can visit if you like, and we're happy to get in touch with the one or the another. Yes, thank you.
Thanks, Jens.
Thank you, Pablo. I welcome you all on this afternoon, the last day of the Vision Fair. And I have good news for all who like it fast. So if you have inspection with a very fast speed, then maybe this is interesting for you. Yeah, here's a quick outline. I want to talk about the problem, then a bit of comparison between line and scan and area scan, then the technology that the solution that we as AIT propose. Then always, when being very fast, light is an issue, and also, yeah, I talk about the FPGA design we did inside the camera to achieve this, and at the end I go to possible application fields and benefits you get with this solution. The problem is there are some processes in industry where you have really fast moving parts or fast moving objects you want to scan, and there normally for fast inspection you use line scan cameras, but also today's line camera technology has a limit around 600 kilohertz or a bit more now, as I have seen. So we thought what we could do. An example is, one example would be rail inspection, so inspection of the surface of rails. Rails are very narrow structures, but you have to go very fast. Or another very impressive example is wire inspection. So for hot wire, speeds between 100 and 150 meters per second. So this is around 400 kilometers per hour, really fast. Is an issue, and when you want to scan at this speed with 600 kilohertz, you get a resolution about 0.2 millimeters, which is not very high because wires are normally very thin. So very thin and very fast is normally a bad combination for normal cameras. And the solution idea is now we profit a bit from the development of area scan cameras. Area scan cameras are a bit further in terms of lines per second they can achieve. We use an area scan camera, but on the output, on the interface to the PC, we make it look like a line scan camera. And with this we can the basic idea is to have a special camera with a sensor that has a 0 frame overhead time, so we can read out the sensor at about 100,000 times per second. So we have order of 100 kilo frames per second, but only a region of interest of 10 sensor lines. So 10 times 100,000 is the million I'm talking about. Yeah, and but the normal issue is that normally those sensors, those fast sensors, have this frame overhead time. So a time that you have to wait between 2 frames because of the internal of the sensor. So it's necessary to have a very special sensor. This is not possible with every sensor, of course, and some sensors have poor performance in image quality if you have run them with too high frame rates. But we have a viable solution here, a viable combination. We have found an off-the-shelf camera, so the camera hardware is not from us. We buy it with it approximately 2K times 1K area image sensor with a very high frame rate. Full sensor can be read out at 2,200 frames per second. This sensor has, as I mentioned, 0 frame overhead time, so it becomes fast if you read out order of 10 lines. And last but not least, the FPGA can also be extended by the customer. Normally, the vendors of cameras don't like that the customers program something inside the camera. In this case, this is possible. And with this, we can also handle some artifacts from the sensor directly in the digital domain in the FPGA. And so we realized a scanner, now it's the question if it's an area scanner or a line scanner, but at the output it's a line scanner with 1 megahertz line rate. Now here's the principle. The principle I explained for a field of view of 4 lines. So we read out from the sensor 4 lines, and we make in fast sequence the images of those stripes of 4 lines. And if we stitch together those blocks of few lines, then we get an image of, let's say, 1,000 lines, which is can be well processed by the PC afterwards. So at the output, it's an area image of order of 1,000 lines, but from the sensor is triggered in the order of 100,000 lines per second. And that's the reason why we talk about a virtual line rate, because sensor side is triggered order of 100,000 times per second, but only at the output, the result is equivalent to a line scan camera of 1 megahertz. Yeah, maybe, I hope you see it. This comes from our first tests. This can happen if you have inhomogeneous illumination. Then you see here some gradient in the brightness. These are stitching artifacts you don't like, of course, but they come from inhomogeneous illumination, and if you have too many lines per block. So it's necessary to reduce the number of lines, and then this effect vanishes. Now, how to illuminate. Also, illumination is not so easy, because 1 megahertz line rate means 1 microsecond exposure time, and there we use the benefit of modern LED technology, because modern LEDs can be strobed very fast. Also, the white LEDs can be strobed with pulse durations in order of 1 microsecond or even below, and that we make short pulses of 1 microsecond and then several microseconds where the LED has time to cool. So this is also called overdrive, and this leads to the effect that we can have during the light pulse. Here is the 1 microsecond light pulse. We can have a really highly intensive lighting with high intensity, which is much higher than if you would turn on the light the whole time for continuous lighting, because in the time between the pulses the LEDs can cool down. Yeah, and then altogether this area scan camera, which is now on the output a line scan camera, together with this fast illumination, of course we have to synchronize very well the camera and the illumination. Oh, something happened. Then you see here the example of the surface of a banknote, a 10 euro banknote, with somebody interferes here. We can, at 10 meters per second, we can resolve this tiny micro writing on the banknote. Do I have to hurry? Is the time gone? Yeah. So you can I can show you this in the demo. The effect is that you see this tiny writing only 0.2 millimeters high, even at 10 meters per second. Yeah. One word to the FPGA design. The camera we used has an infrastructure that the green box, this is the complete FPGA, it can be programmed by the user. Of course, the user must have skills about FPGA programming, so Vivado tools and VHDL or Verilog. The infrastructure looks in this way, that there is an IP block, two IP blocks from the vendor of the camera. You can't change, and you have to live with all signals that come out and go into these gray blocks. This is the vendor IP for the sensor control and for the interface. But in between, you can have your own, you can design your own FPGA processing. You can do fine things of very fast image processing inside the FPGA. And in this custom IP, we realized this fast stitching. And also the triggering. Also, you have also trigger signals, the trigger signals available, so we also realized the synchronization with the illumination. So, yes, this is, we used high-level synthesis in our design, so the high-level synthesis result looks like this. Here you see a floor plan of the complete FPGA. You see it's 2/3 are already used now, but there's still room for further algorithms inside. Yeah, and here, this is what the demo looks like on the right side. Sorry, this was me. Yeah, we have the benefit, as you see, is you have a camera resulting with 1 megahertz line rate, and you can use an off-the-shelf camera to realize it. Yeah, the application fields are in high-quality metal inspection, wires and cable. Sorry. Can it be stopped also? I don't know. Inspection of infrastructure like rail or road surface, print inspection, also color is possible. Then inspection of battery electrodes you can combine it also with photometric stereo, as you see it here, and PCB inspection and many other where speed is important. So I come now to the end. With this talk, I conclude that we demonstrate here the ability to scan with 1 megahertz line rate or even more, and this is enabled by fast area scan technology available on the market, and also fast LED strobing technology, and hopefully there's much benefit for the industries who need that speed. Thank you.
It is yours.
Thank you so much. I'm Juraj. I work at the image processing department at Fraunhofer, and I work in the virtual inspection group. So what we do is we do inspection, but in the synthetic domain, in a virtual domain. And today I would like to talk about some prospects that deep learning can use by using synthetic data for the surface inspection in this case. So there are several challenges when we want to automate visual inspection. So we specifically focus on metals because they have high reflectivity, they are highly problematic, industry doesn't know how to handle them properly. And metals, depending on how they were produced, depending on what their functionality is, they can have different kind of surfaces that have very interesting patterns. The problem is if you want to automate something, these patterns produce false positives, and this introduces problems. Another problem is depending on what kind of product you have, what kind of needs you have from the product, what kind of quality levels you expect. You have to tailor the inspection specification to your specific needs. So it depends on the object geometry, on the type of defects, how strong the defects are, and similar. There is also a diversity of defects. So we have defects that are geometrical, defects that are purely surface-based, like some sort of impurities. or we have simple stickers. The question is which ones are defects, which are not, which should be ignored. This is again up to the specification, but our recognition models need to handle all of those nonetheless. And yeah, once we start developing the recognition models, we run into a lot of more trouble as we go along. So when we try to automate, we basically have kind of two scenarios. So we either have a small data set at our hand or we have a big data set. Here we actually assume that the inspection setup is already made and we can actually collect some data from it. This is like down the line, up the line from us. So yeah, so a common thing is we have a small data set, and if you are very lucky, you are in a common domain, so you can find some additional data, you can collect a huge data set, train your model on that, and then just fine-tune it on the target data, and this usually works pretty nicely. But sadly, more commonly, you are in an isolated domain, you're working on something highly specific, highly new, and there is no other way than to use the handcrafted methods. At our department, we actually have tools for that as well, so we have some experience with those projects as well. But when we are talking about large data sets, we usually talk about supervised learning. So you have a lot of samples that are clean, correct, and you have a bunch of defected samples, and then you just train a recognition model on that. You separate the good from the bad, and this usually works if you have enough data. If you have a lot of data, you can probably also collect more. But we are more interested in the scenario which is industrially more interesting because defects are rare. Defects are hard to acquire, especially the hard defects that are highly dangerous. So usually we have an abundance of only okay samples, so only correct products. And then what we do is basically we just train the model to learn what is okay and ignore the rest, or report the rest. And for the purpose of this talk, I will focus on this, although we actually, as you will see later, we can also handle the isolated domain. So arguably the most popular algorithm for anomaly detection is patchcore. It is relatively new, and it is quite cool because it only learns what is okay. You only give it the data so that it knows what it should learn to ignore, and then everything else is reported as an anomaly. And the cool thing is that you can reuse pre-trained models, so not a lot of training is required, and everything is fun and games until you start running it on large data sets and large images, and then it's game over. So it has a really high memory consumption. A lot of industry colleagues were complaining about that. And basically it restricts you to either using small data sets or using small image sizes. So if you have a huge image, you patch it up into small areas, and then you train like multiple recognition models for each of the areas separately. So what we presented last week on ECCV was a sequential version of the patchcore. We just inverted the algorithm. So we just use the memory that we require at the moment, and we update the model just as a usual recognition model. And what we could basically apply it to is large image sizes, and on running it also on consumer hardware. So I was actually running it on a small laptop as well. And additional benefits, what we could use was we could actually train these models like in parallel on different parts of the data sets, train them to collect the knowledge. And then because of our inversion algorithm, we actually can design a really fast transfer learning method, which we call core set melding, which just uses the core sets and melds them together, so you combine the knowledge in a highly explicit way. So this is like a common way that we talk about deep learning. So we focus on the model, and we know that feature extractors are important because if you extract good features, the recognition is easy. You just draw the line and it kind of works. And this is common for a model-centric view. So you focus on the model, and if you can control it, you can control the performance on the recognition task or whatever you want to apply it on. However, the problem is that when we talk about good features, we are subjective because good features are dependent on the task that we apply it on, and it's not so reusable. It's not completely reusable. But some features are generic enough, so like simple edge detection or some contour recognition or highlighting, so some things can be reused. And this is kind of why these methods actually work with ImageNet pre-trained models. So there are general features, but there are features lacking. And the most important part in the whole story that is often being ignored is actually that the data is the stuff that we train our models on, and the data is actually influencing it a lot. So the data-centric view is where we say, okay, control the data and you will control your model and thus the overall performance. And some examples how you control the data, well, you target the weaknesses in your data sets. So you have usually an imbalance between defect types. So we have an abundance of okay samples usually, and defects are quite much rarer. And some defects are so rare that you maybe have like 1 or 2 samples of them in a data set of 100, for instance. You also have to learn to ignore a background. So once you deploy a model in a factory, what is oftentimes a problem for recognition systems is there is a cloud coming on, so the lighting changes on the day of the year. You have people walking, producing shadows. You have objects that the products are placed on. They have wear and tear as well, and they can also confuse the models, so they need to be ignored as well, and you have to handle it somehow, right? Another problem is that you have misalignment. So if you have perfect alignment, that's good. Usually this is quite expensive. So you want to focus more on more robust algorithms and recognition systems that don't care about small misalignments and still works quite well. And we also have contaminations. So this is stuff that happens to be on the surfaces of the objects. So the simplest thing is like a dust bunny. So it's just like a piece of fabric that falls onto the object, or dust, or quite often we also have soap residue and water stains on them, or droplets of water and oil, quite common ones. But the problem is, how do we target these weaknesses? Because we just said before that it's hard to acquire this kind of samples. So we have kind of 2 questions. So how do we even acquire enough of these rare samples to target these weaknesses in a data-centric view? And how do we even acquire the edge cases, which are so rare that are you know they are theoretically possible and they are really dangerous, but you have no idea how to produce them. So collecting the data is quite expensive. Like if a defect happens once in 10 years, then yeah, that's quite expensive to train a robust model. If you want to do a data augmentation, you can do it. It helps. We proved it also, but the data augmentation is limited. You can only do certain stuff in the image space. If you have certain misalignments that are so radical that the reflection of the surface changes, you cannot do data augmentation there. You have to use the 3D domain. And generative models are quite popular. They do help. So if you train a model, if you have enough data to train a generative model or fine-tune it from something pre-trained, it helps. But the problem is it produces hallucinations, and this is proven on and on again. And the second problem is, how do you generate out-of-distribution samples? So if something is so rare that the model sometimes can generalize to it, but can you really adjust it to your specific needs? From the current papers, it is really hard to find a model that can really do that. And one of the major problems is also that there is not enough industrial data out there to actually train a decent foundation model for generative models. So we are kind of stuck between these choices. Well, we actually found another solution, much older, all the way back to the 90s and 80s. So we use rule-based synthetic data, which is another way to say that we use something that uses computer graphics and rendering. So when I say rule-based, rules are actually just physical models that we use to reconstruct the reality that we see around us. So like the surface textures, the geometry of the object, the reflectivity and the simulation of light, these are all kind of models of reality that you simulate to ensure that your data will be clean. And another thing that we found out was it actually helps you to experiment quite precisely. So you can just change a single variable, keeping all of them rest, and see how it affects the model. So you can effectively learn what works and what doesn't. And when I talk about the control that you can have, well, you can have a control of the geometry. So we start basically from a CAD file or any kind of geometry representation. And you can also embed like geometric defects on those. You can add product variations quite easily and produce multiple data in this way. You can control it to your liking. We can also model the texture. So we can apply different kind of textures that have physically correct reflectivity patterns. And we can also control the environment, so like what is around the camera, is there some light leaking from the sides, where do we position which equipment, which cameras do we use, what are the parameters. We have control over everything, and we can change them one by one. So there are quite a lot of benefits to using this synthetic data. One of them that is quite staggering is that it is highly reusable and adaptable. So last year we published a dataset on a metallic clutch where we applied our models to a curved surface, and this year we just adapted basically the same model to a flat surface, just tweaking parameters so it matches the machining process of those models. We can generate following a tight specification because computer graphics is actually kind of notorious for being too perfect. So if you have a really tight specification, we can generate it. We can generate variations up to your specifications. So if you need to handle a certain number of millimeters offsets, we can generate this without problems. We have effectively infinite variability because we use procedural modeling, which is a fancy way to say that we model everything with functions. And we can generate an abundance of very unique samples very quickly. We also have infinite resolution, although a small disclaimer here. So you have the resolution as much as you invest. So as deep as you want to scan into the surface, as much as we can model, right? We are covering edge cases because if you have a theoretical edge case that is really hard to deliberately produce, or you haven't caught it so far in the production, but you know this could be a serious problem, we can generate it. Because we use everything explicitly, we just use regular 3D modeling or whatever kind of method you want. It is quite explicit, you have direct control over everything, and you can use it directly. And quite important for the industry that we found out was we have consistent quality, so there are no hallucinations in our models. The models are a replica of the reality, and they produce, so we fit them and we develop them by observing microscopy data or just macroscopic data, and we can tweak the parameters to make it look more correctly, but the physical model is the reconstruction of the manufacturing process itself. However, as it is with synthetic data, we do have domain gap that is present because our models are just models of the reality. It's not the whole thing. So we cannot model some maybe higher frequency details or some specific stuff. But so far, what we saw is just simple fine-tuning works pretty well. We tried different kind of domain adaptation methods as well, but fine-tuning was by far the easiest and the best one in the field. Thank you for listening. If you want to learn more, you can check out our project website. We have also different we work on different stuff. We also work in the volumetrics as well. If you have a special use case that you think we cannot handle, we would be really happy to listen to you and see if we can do something about it. And if you want to track some following research that will come in the next couple of months, maybe, you can also follow me on Orchid. And yes, thank you for listening.
Thank you, Pablo. Hello, dear people of the Vision. I will tell you a bit about a project that we did, an industrial inspection project regarding batteries. So, to motivate this, batteries is a well-known thing. You know, when you're doing a battery, you always start with some substrate. You have, of course, an anode. You have a cathode. You mesh them together, put in some electrolyte, and bam, you have a battery. It's a very old application. As you see, this is one of the first electric vehicles. At some point, they were on the verge of overtaking the automotor, but now we are there again. So, how do you create one battery? So, as I said, you need some material that makes an anode or a cathode. For the cathode, it's usually quite some bad stuff, nickel, manganese, cobalt, stuff that you want in long term to get rid of. But of course, right now we have it. So you mix up all those materials in this dark slurry, and you then want to apply it on the substrate foil. So this is like it's copper. It can be copper. It can be aluminum. For this cathodes that we're looking into, it was aluminum. And you have a sharp knife. You pull the substrate over the depot. You have You have a knife that applies the whole thing in a defined thickness on the substrate, and at some point you have to dry it, so it will stay on the substrate. Next thing what you do is you push it together, you mash it together to get a real homogeneous coating, and then you can cut out some one of these small patches. All of them have the tabs, and those tabs are then what you see then later on this kind of battery. Then you don't not only have one kind of thing, one anode cathode combination by yourself. You stack it up on top of each other to increase the capacity. And the last thing that you would want to do is just fill in the electrolyte, break it in, and you have your battery. It's not that hard. Maybe nothing you would want to do it at home, but you could very well if you have the materials. So we are concentrating on this in this project. We concentrated on this coating and drying phase. This is we have colleagues of us are doing a battery research lab, and the need is to quantify how good are they. They're changing materials, they're changing formulations, they have different kinds of chemistry, and now the question is, how good is it? Of course, they can do analysis on the micro level, which they do, but they always have like at most one fingernail full of patch of your material. And if you want to really quantify it in a broader size, you would want to see for it in at larger scales, and this is what we did. So to motivate those, this is two images of the cathode we looked in. And when you're doing direct measurements, it's dark material. It's just a black patch, and you will suffer from in an intensity image from not seeing too much, because there's a lot of structure involved in the material. And if you want to see like minute details that you minute details or minute defects that you would want, you rather would want to use photometric stereo. And this patch, this figure on the right side reveals there was this one wrong streak. I will come to it back, because there's some different kind of very specific defects that you will get when you're coating batteries. So, as I already said, dark surface material is an issue, especially if you want to go then in scale up and you want to do it. And I think in the industry you say it's the gigafactory scale, you know. There you have running speeds of at least 2 meters per second, 4 meters per second, and you want to have like resolutions of like down to 25 microns per pixel. So this is a quite high-speed process. And it also means that that the algorithm that you're working with has to be able to keep up with the speed. And photometric stereo is something that you see at our booth, but also in then of our other exhibitors, quite well suited for that. So here again we have a nice depiction of this coating process. As I told, there's the knife, there's the depot, there's the drying part. In the end, you collect the roll for calendaring, and what we did was to introduce one of those photometric stereo systems right at the end of the drying stage, which is a quite good place to do it. Yeah, so let's go with that. Just one slide overview of photometric stereo, specifically the Lambertian case, just a academia foil, because it's a very nice algorithm that you can summarize very well on this one slide. So you have like this camera, you're looking down on your surface, and you have several light sources. And when you shine a light from the light source on the surface and it hits the camera, you will get some intensity reading. And when you move this light source to some other direction, maybe to that one, you will get your intensity reading will be brighter. So now, when you do it several times, at least 3 times, you can compute the surface slant. So where does this particular piece of surface look into? just from this from these readings, and you will also get not only the surface itself, but also the albedo, which is basically the not the color, but the intensity response of your material without the slanting effect. And this is exactly the algorithm that we used. We developed one of an acquisition setup specifically for those anode foils. Here you see the setup in the lab. There is this there's a roll on which we put up one of those samples. We have readings from it for different sites, and then we turn up when we run this through this algorithm, come to this bluish, reddish, violet image where each of the color channels, the red, the green, and the blue one, represent the vector, the normal vector that you will get from the algorithm, but because these are a bit hard to interpret if you're looking at it, we are usually using the surface gradient, which is basically just the change of the vector, of the surface vector from one pixel to the other. It gives you like a gray image where if everything is standard gray, nothing is happening, the surface will be totally flat, and if something goes up, it will get white, and otherwise it will get black. So this is more or less how to interpret those images that you see here. We started with this laboratory setup, and this was the specifications were like at 50 microns per pixel or 20 microns per pixel, and it was going like for half a meter per second, which was for the lab setup quite okay, certainly sufficient. But then within an EU project, we had this requirement, okay, what is when you want to go deeper? If you want to have like more detail, for one, can you go faster? Yes, we could. We could go for like 2 meters per second, and then another thing would be the other question was like, okay, can you go it at 10 microns per pixel? It does work very nice, but the one trade-off you do, and this is one of the issues you have with all the other exhibitors, optics is a trade-off game. If you gain something on one hand, you lose it on the other, and what you lose here is the field of view. So you only have like a 5 centimeters ratio, but for that it works very well. You can see the setup here, right here, and the variation of that is also seen. It's distributed now over those two to demonstrate. It has been a while back. So what kind of defects did we see? We saw pinholes. Pinholes is like very small porous locations strewn over the foil, and you should get something a reading like that. So the albedo of that of this here is dark. You have these small dots, and it turns out those small dots don't always coincide with the pinholes that you get. I have to qualify here. Pinholes is if you ask a guy who does battery chemistry, will say, oh no, you need that. You need some porous stuff. So your electrolyte can get into the anode, but if you have like bigger holes, this is an issue. So this is a very nice thing. By the way, I always had to ask my colleagues for the worst samples they could do, and of course this is something a battery chemist wouldn't want to give out. So I'm very happy for them to give them to me, and this must be one of the most interesting ones. This was a hand-coated thing. This is what can happen if you do it by hand, and you see that you have all kinds of defects that you have here. You have like this lava, this crater landscape. You have the cracks, which you don't want, and one of the biggest. And you also have like agglomerations and so on. This is something that you really don't want. So we quantified what we got from our colleagues, and we arrived at at 4 different kinds of very common defects. The first one would be the agglomerations. You saw it in the crater landscape. This is a real bad kind of defect because it stands out. And if you have like some of this spiky stuff going out from your electrode and you stack it together, it can happen that it can pierce the substrate material. The whole battery will give you like a electric short, and then it will burn down maybe a house. I don't know, a ship. You don't want that. This is the one defect that you really don't want to have. Then you have the cracks. So when your formulation is not really correct, then you will get those kind of cracky stuff. Is also stuff that goes up. The other thing is cavities, which result from very small bubbles that burst and leave these quite nice craters. Also an issue with the formulation. And then is the blade trails. Blade trails is a very profound thing. So we talked about the knife. If one of those, if the formulation is not very perfect, you have like something like some little stone in it, then it will clog the knife, and then you will have a trail where you have not so where you have inhomogeneous coating. And of course, we collected that. We annotated some of us 26 of those sets to give you a large amount of different images and quantify them. This is an example of the mask, and I don't want to go too much into the detail about the model because it's rather stock ResNet a model with that's well known. The one thing that we did was we didn't use the intensity. As I said, we used the gradient or the XY vectors of our reading with that, and came down to results that look like that. So we have like here's some blade trail. Here was an annotation. This was the result, and we're doing like pixel level segmentation here. And in the end, we came to classifier that can for 99% get correctly identify good defective parts. And the other thing is you also don't want and you also don't so you don't want to have you want to have a very small false negative rate, which is also given here. False positive rate. So you don't want to have when you have a lot of material going on, you don't want errors when there are none, because this will disturb your production thing. So going together, I showed you a use case of an inspection system for battery electrodes. We tested it up to 2 meters per second, albeit with a very small field of view, but nonetheless. It can be used in those kinds of machines, and it can stream you out like these other devices that we have here, the defect data. And we also saw that that photometric stereo works quite well with those kind of surfaces. And in that, I think you don't have to read all of this, but just in case, I say thank you, and I'm up for your questions.